In this video, we're going to discuss telescoping series, which are a very particular type of series for which we'll be able to write down a formula for the partial sums and therefore use the definition of series convergence to determine whether the series converges or diverges. Since we'll be using the definition of series convergence, we should recall that quickly. We say that the series from n equal 1 to infinity of a sub n will converge to the number s, or equal s, if and only if the limit as k goes to infinity of the kth partial sum s sub k is equal to s. Here, the partial sum s sub k is just the sum of the first k terms of our series. So let's take a look at a classical example of a telescoping series. In this example, we want to determine whether the series from n equal 1 to infinity of cosine of 1 over n minus cosine of 1 over n plus 1 converges or diverges. In order to do this, we're going to first find a formula for the partial sum s sub k. In this series, our term here, a sub n, is going to be cosine of 1 over n minus cosine of 1 over n plus 1. And so s sub k is the partial sum of the first k terms of this summation. And so this will simply be a1 plus a2 all the way up to a sub k. And so we're adding the first k terms together. And using our formula for a sub n, we can compute each of these terms. A sub 1, for example, is what we get by substituting 1n for n into this expression for a sub n. So we get cosine of 1 over 1, which is cosine of 1, minus cosine of 1 over 1 plus 1, or cosine of 1/2. And so here we have our first term, a sub 1, in our partial sum. We're going to add to that the term a sub 2, which will be cosine of 1 over 2, minus the cosine of 1 over 2 plus 1, which will be 1/3. So we have a sub 2 being cosine of 1/2 minus cosine of 1/3. We can go ahead and do maybe a 3, which will be the cosine of 1 over 3 minus the cosine of 1 over 3 plus 1, which will be 1 over 4. And of course, this will continue. We'll add up all of these until the very end. We'll have a sub k, which will become cosine of 1 over k minus cosine of 1 over k plus 1. So now that we have our partial sum s sub k completely written out, if we look at this carefully, we'll notice that a lot of these terms will cancel when we actually add all of these things together. For example, in the very first term of a1, we have a negative cosine of 1/2. And in the term a sub 2, we get a positive cosine of 1/2. And so when we add those numbers, all of these numbers together, the cosine of 1/2 and the negative cosine of 1/2 will cancel out completely and leave 0 remaining. We get the same thing happening with the cosine of 1/3. We have a negative cosine of 1/3, and then we add a positive cosine of 1/3, and those will completely cancel out. And this cancellation pattern will continue. The next term here is our negative cosine of 1/4, and this will cancel out with the positive cosine 1/4 that will appear in the term a sub 4, which we don't have written here, but is part of the dots that are indicated that indicate the pattern continues. When we get to the very last line, the cosine of 1 over k will cancel with the negative cosine of 1 over k from the previous summand, in particular a sub k minus 1. And so here we have all of these cancellations. Everything will cancel, and only two terms remaining. We have a cosine of 1 and a negative cosine of 1 over k plus 1. And so here what we've seen, by collapsing this sum, we see that s sub k is equal to cosine of 1 minus the cosine of 1 over k plus 1. And this is true for any value of k, regardless of whether k is 1, whether it's 2, or whether it's 500. We've reduced the formula for the partial sum s sub k down to 2 terms. This collapsing behavior is why this is called a telescoping sum. It behaves much like an old-fashioned telescope where you can push the ends together and everything in the middle collapses to make a much smaller object. Here we have this sum with a lot of terms, and with the cancellation, as we've seen here, we get a lot of collapsing and we have just 2 terms remaining. To determine whether our series converges or diverges, we simply need to determine the limit of this sequence S sub k. So we want to find the limit as k goes to infinity of this partial sum S sub k. So we'll do this by using the formula that we just developed for S sub k. So we want the limit as k goes to infinity of cosine of 1 minus cosine of 1 over k plus 1. And now we have the limit of a difference. And using limit laws, we can rewrite this as the difference of the limits. Now notice that cosine of 1 is a constant. There's no k involved there. And so when we take the limit of a constant, we just get that constant back. So the limit of our first term is just going to be cosine of 1. In the second term, we have the limit as k goes to infinity of cosine of 1 over k plus 1. And we note that cosine is a continuous function. And so when we have the limit of a continuous function of a sequence, we can pull that limit inside the continuous function, and in this case get the cosine of the limit as k goes to infinity of 1 over k plus 1. And we know that 1 over k plus 1 will go to 0 as k goes to infinity. And so our partial sum, the limit of our partial sums, will be cosine of 1 minus cosine of 0. And of course, cosine of 0 is equal to 1. So we end up with a partial sum with a limit of cosine of 1 minus 1. Since this is a perfectly fine number, this shows that the sequence of partial sums, S sub k, is a convergent sequence, and therefore our series that we were considering in this example, the series n equal 1 to infinity of cosine of 1 over n minus cosine of 1 over n plus 1 is a convergent series, and it converges to the sum of cosine of 1 minus 1 because this is the limit of the partial sum, sequence of partial sums for this series. So we have a convergent series with a sum of cosine of 1 minus 1. If you'd like to try a similar example, you can pause the video and determine whether the sum from n equal 1 to infinity of e to the 1 over n minus e to the 1 over n plus 1 converges or diverges. Resume the video and the full solution will appear in a few seconds. Letting a sub n be the given term of our series, we know that the partial sum S sub k will be given by a1 plus a2 plus ... all the way up to ak. We substitute in n equal 1, 2, up through k into our formula for a sub n, and we obtain the sum e to the first power minus e to the 1/2 plus e to the 1/2 minus e to the 1/3 plus e to the 1/3 minus e to the 1/4 plus e to the 1/4 minus e to the 1/5, and our final term will be e to the 1 over k minus e to the 1 over k plus 1. At this point, we see a lot of cancellation happening here. We have a negative e to the 1/2 and a positive e to the 1/2, so those will collapse on each other. We also have a negative e to the 1/3 and a positive e to the 1/3. We have a negative e to the 1/4 and a positive e to the 1/4. And at this point, we can see the pattern that's happening. This negative e to the 1/5 will cancel with the positive e to the 1/5 in the next term that's not shown. And jumping to the end, the positive e to the 1 over k will cancel with the negative e to the 1 over k that will appear in the previous term. And so once we have all of this, everything collapsing, we see that we have only 2 terms remaining, e to the first power, which is just e, and negative e to the 1 over k plus 1. And so e minus e to the 1 over k plus 1 is our formula for S sub k. We then take the limit as k approaches infinity of our sequence of partial sums, s sub k. So we want the limit as k goes to infinity of e minus e to the 1 over k plus 1. This exponent, 1 over k plus 1, as k goes to infinity, this exponent will go to 0 because the denominator of the exponent gets very large. And so here we have a limit of e minus e to the 0, and e to the 0 is 1, so our limit is e minus 1. Since our sum of our series is defined to be the limit of our sequence of partial sums, the series n equal 1 to infinity of e to the 1 over n minus e to the 1 over n plus 1 is going to be e minus 1, and therefore this series converges. In this example, we want to determine whether the series from n equal 1 to infinity of 1 over n times n plus 2 converges or diverges. This doesn't necessarily look like a telescoping series based on the form that we're given. In previous examples, the telescoping series had terms which were differences of expressions, and that allowed for cancellation when we found the partial sums. But here, we just have a single term, 1 over n times n plus 2. However, since the term of our series is a rational function, 1 over n times n plus 2, we're able to use partial fractions to rewrite this as a sum of two simpler fractions. In this case, if we carry out that process, we'll obtain the partial fraction decomposition 1/2 over n minus 1/2 over n plus 2. And so this here is our using partial fractions to do this. And we obtain this new expression, which is equal to the term of our original series. We can then simplify this just a bit. 1/2 over n can be written as 1 over 2n, and 1/2 over n plus 2 can be rewritten as 1 over 2 times n plus 2, which if we distribute the 2 will become 2n plus 4. And so this is another way of writing our series term a sub n as 1 over 2n minus 1 over 2n plus 4. And using this formulation, the nature of this series as a telescoping series will become very obvious when we try to write down the partial sums for our series. So we can rewrite our series n equal 1 to infinity of 1 over n plus 2 as the sum n equal 1 to infinity of 1 over 2n minus 1 over 2n plus 4, and we'll call the terms in this latter expression a sub n, since they have a difference, since it involves a difference, and this will allow us to use the telescoping series approach. We want to find a formula for the partial sum s sub k, which we know will be a1 plus a2 plus a3 and so on, all the way up to a sub k. And maybe we'll throw in the second to last term here as well, because that will be useful in this example. So we'll have a sub k minus 1, and then finally a sub k. We can compute each of these terms by substituting the subscript in for n into our formula for a sub n. So for a sub 1, we're going to let n equal 1, and we're going to get 1/2 minus 1/6. So 1 over 2 times 1, which is 1/2, minus 1 over 2 times 1 plus 4, which is 1/6. So our first term, a sub 1, is 1/2 minus 1/6. When we substitute 2n for n to get a sub 2, we're going to get 1/4 minus 1/8. When we substitute in a3, substitute 3n for n, we're going to get 1/6 minus 1/10. We'll do one more term here. We'll do a sub 4. When we substitute 4n, we're going to get 1/8 minus 1/12. And then we'll jump to the end. We'll do a sub k minus 1. So this will substitute k minus 1n for n. And so we'll get 1 over 2 times k minus 1 minus 1 over 2 times k minus 1 plus 4. And that ends up being just 2 times k plus 2. And our last term, a sub k, we're going to get 1 over 2k minus 1 over 2k plus 4. We're just replacing the n with k here. And that is the end of our partial sum. That includes all of our terms from a1 up through ak. And now if we look through here, we don't get cancellation quite as frequently as in the previous examples, but we do get some cancellation nevertheless. We have a negative 1/6 here, and that cancels with the positive 1/6 of two terms ahead. So our negative term in a1 cancels with the positive term in a3. Similarly, the negative term in a2, the negative 1/8, will cancel with the positive term in a sub 4, the positive 1/8 there. And so as we continue, we'll see that negative 1/10 will cancel with the positive 1/10 from the term a sub 5, which we don't have written, but will certainly appear in this series. And similarly, the negative 1/12 will cancel with the positive 1/12 in the sixth term, a sub 6. Now jumping here to the end, we're observing that all of the positive terms of our in each of these summands cancels with the negative term from two terms earlier. And so 1 over 2 to the k minus 1 will cancel with the term being subtracted in two summands earlier in our sum. And likewise, 1 over 2k will cancel with the negative 1 over 2k, which appears two terms prior in our partial sum. Once we have this, we notice we actually have four terms that are uncanceled. And so our partial sum here, s sub k, will be 1/2 plus 1/4 minus 1 over 2 to the k, or 2k plus 2, minus 1 over 2k plus 4. And so here we have four terms in our partial sum. We want to take the limit as k goes to infinity in this partial sum. And so we want the limit as k goes to infinity of 1/2 plus 1/4 minus 1 over 2k plus 2 minus 1 over 2k plus 4. And as k goes to infinity, we know the two terms here with the k in the denominator will go off to 0. And so we get a limit of 1/2 plus 1/4, which is equal to 3/4. So our original series that we started with converges, and it converges to the value of 3/4. If you'd like to try a similar example, pause the video and determine whether the series n equal 1 to infinity of 1 over n plus 1 times n plus 2 converges or diverges. Resume the video and in a few seconds see the full solution. Using partial fractions, we can rewrite the term of our series, 1 over n plus 1 times n plus 2, as 1 over n plus 1 minus 1 over n plus 2. We can then compute the partial sum of s sub k as 1/2 minus 1/3 plus 1/3 minus 1/4 plus 1/4 minus 1/5 plus 1/5 minus 1/6, and so on, ending with 1 over k minus 1 over k plus 1 plus 1 over k plus 1 minus 1 over k plus 2. We then can cancel here with several terms. We have a negative 1/3 and a positive 1/3, a negative 1/4 and positive 1/4, negative 1/5 and positive 1/5. This negative 1/6 will cancel with our next term, which will start with a 1/6. Going to the end here, the 1 over k will cancel with the negative 1 over k in the previous term. We have a negative 1 over k plus 1 plus 1 over k plus 1. And this leaves just two terms, 1/2 minus 1 over k plus 2. We then take the limit as k goes to infinity of this partial sum. We know that 1 over k plus 2 will have a limiting value of 0. And so we're left with the sum of our series being the limit of our sequence of partial sums, which is 1/2. And therefore our series converges to 1/2.